Hello everyone, I am Ching Yao Hong from Academia Sinica. Today, I am excited to introduce our recent work titled Attention Discriminate Sampling for Point Clouds, which was a collaborative effort between Yuing Cho, my advisor Ting Lulu, and myself. Let us begin by discussing the motivation behind this work. Point cloud sampling is an essential step for designing practical solutions to the respective 3D computer vision applications. While existing techniques mostly rely on utilizing distance-based geometric information to yield efficient sampling, their main drawback is the lack of consideration of both the semantic and the structural aspects of the underlying point cloud distribution. We aim to introduce a cluster-based formulation that leverages the proposed discriminate attention analysis to implicitly achieve structure-aware point cloud sampling. The motivation is inspired by an attractive observation that point cloud sampling could better represent the original raw data if information about the structural components and complexities of the underlying object has been made available. In practice, the structural information is often not present. However, it is reasonable to group the points into clusters and design an efficient cluster-based sampling scheme that is designed to conceptually approximate the above-mentioned ideal case. To simultaneously explore the semantic and geometric properties of a point cloud, we introduce attention discriminate sampling that leverages feature similarities with spatial relationships to select those points that are representative in both aspects and induce less redundancy. The proposed ADS first divides a point cloud into clusters and enables the algorithm to consider sampling at point-wise and cluster-wise levels. Our method then calculates self-attention relations of the points within each cluster and between clusters to determine how the sampled points are distributed among the clusters. Unlike other attention-based 3D approaches that only consider the points within each subset obtained by farthest point sampling, ADS assesses semantic and geometric relations of the points locally and globally and utilizes these self-attention responses to achieve effective and representative point cloud sampling. Beginning from the problem setting, we represent a given point cloud as a set of 3D points. P equals a set of pi, for I from 1 to n, and n is the total number of points. As n is typically large for most applications of interest, our goal is to establish a general and effective sampling scheme to extract from P an n-point representative subset. The first step of our approach is to divide a point cloud into clusters. We consider mean shift clustering to group the points set into distinct modes and take these cluster centers as the initial seeds for subsequent analysis. The practical outcome is far from the ideal case in that these clusters are obtained solely based on the geometric relation of distances between points, but neglecting the semantic relation from the underlying features. Nevertheless, the procedure of point grouping enables our cluster-based formulation and plays a central role in the proposed attention discriminate sampling. The resulting K clusters empower designing attention-driven sampling beyond the point level. Specifically, we connect the sampling strategy with two aspects of self-attention, within cluster between cluster. It turns out that the two kinds of attention responses are informative for deciding how our algorithm achieves point cloud sampling. The within-cluster self-attention reflects the semantic complexity entailed by the learned features of points within each cluster. The between-cluster self-attention reveals the semantic similarity between clusters. Based on our analyses of cluster discriminate attention, we determine the number of points to be sampled from each cluster C via calculating the following sampling ratio. The number of points to be sampled from cluster C can be denoted as MC and equals M times WC. We carry out cluster-wise sampling according to a decreasing order of MC. Consider now for cluster C, the MC points to be sampled will be chosen from NKPOC, and the sampling within each cluster begins with the most attending point and then proceeds in the least attended point fashion. We express the total loss of learning ADS by two regularization terms and targeted downstream loss. The network architecture of ADS is similar to PointNet++, which adopts state modules. We present the experimental results of ADS on several 3D downstream tasks, such as object classification, semantic segmentation and part segmentation, and object detection. ADS achieves competitive performance with other approaches. ADS exhibits less performance degradation in both classification and reconstruction experiments when decreasing the sampling ratio. The outcomes indicate that the sampled points by ADS are more representative than those by other techniques. To verify the usefulness of the various components in our method, we conduct an ablation study and report the findings in tables. As the qualitative comparison shows, the segmentation outcomes by ADS reveal more details about the scene than those by the standard PointNet++. In summary, driven by the cluster-based design, ADS provides a general solution for 3D point cloud sampling and applications. While this concludes my presentation, for further investigation, please refer to our paper for detailed ablation studies and analysis. Thank you for your attention.